Well, we are at 12 noon, so welcome, ladies and gentlemen, to the September edition of Coffee with Kalepi. My name is Mary Olson, and I can say that we are delighted that you are with us today to learn about domestic hot water return design, featuring our guest speaker, Christoph Lohr. More to come on today's topic, but let's talk housekeeping for just a moment. Okay, audio troubles. Well, likely you didn't hear me say that, but if you see this slide, note that simply exiting the webinar and returning is a helpful anecdote. As well, the GoToWebinar does offer a technical support number that you are free to call. You'll see that on your display. Following the webinar, you will be given the option to receive the slide deck. Simply answer yes in the post-webinar survey. And a friendly reminder, our webinars are posted to YouTube for your listening convenience. Watch for that within about a week or so, should you like to listen in again. Kalepi also provides a certificate of attendance. For those of you who are requiring continuing education verification, the certificate is automatically emailed to you after the webinar. You don't have to do anything in order to ask for it. Okay, the latest edition of Hydronics has hit the streets. If you are not familiar with Hydronics, may I tell you a little bit about it? It's a complimentary design journal provided semi-annual to our subscribers. It's written for industry professionals to aid them in system design, component application, and selection. This plumbing-focused edition will assist the reader in evaluating heat pump water heater technology while investigating the advantages and also the limitations in both retrofit and new construction. Watch for the subscription link. We'll share that in the webinar chat box during the webinar, should you be interested in receiving your own hard copy. If you're a digital person, don't worry, we've got you covered. We have a completely interactive edition at hydronics.kalepi.com. Make sure to check it out. And you'll also see several other editions where you can interactively search and research an edition. Will you be attending the ASPE Technical Symposium next week in Seattle? We will be there, booth 501. Please be sure to stop on by. We would love to meet you real time. As well, Max Rohr, our Kalepi Education and Industry Engagement Manager, and may I say, recently named Next Gen All-Star by BNP Media as a young professional to watch in the plumbing industry, will be at the head of the class on Friday, September 29th at 1:30, discussing mixing and balancing valve selection for domestic hot water apps. And if I may brag on our guest speaker, he will also be at the symposium. Christoph will be speaking about hot water return engineering, the theory, practice, and future trends on Saturday, September 30th at 10:45. It's another great reason to attend the symposium and hope that you can join. Okay, get your pencils out in your calendars. And if you are curious about next month's Coffee with Kalepi webinar, we've got a very cool contractor-focused edition in which we are featuring our Ask Kalepi team, and they will be joined by Matt Lebo of Green Point Plumbing, who's out of Somerset, Mass. And they will be covering the ways to keep systems running at peak conditions when the heat is on. Count on this webinar to be educational and, might I add, entertaining. Okay, and without further ado, may I introduce Christoph. He is IAPMO's Vice President of Technical Services and Research, and as part of his duties, he provides industry leadership through participation in strategic industry initiatives. Christoph has over a decade of experience in designing plumbing systems. He has a reputation and, may I say, a passion as a results-oriented expert, particularly in the realm of balancing waterborne pathogen prevention and water sustainability. He is a distinguished graduate from the Virginia Military Institute and holds a Bachelor of Science in Mechanical Engineering. And Christoph, you have so many letters behind your name, the alphabet soup of credentials. So take it away, Christoph.
Excellent. Thank you so much for the warm introduction, Mary. And thank you to all of you that are tuning in to show up for this. Absolutely excited to see so many people that are as passionate as myself, if not more passionate, about trying to do the right thing with hot water return systems, which is definitely seems to be a big mystery or a big topic, maybe let's say, and how to approach this correctly. And it's interesting for me, my story in terms of domestic hot water return systems, it starts actually back in my college days at the Virginia Military Institute, where I had the fortunate privilege of having a really great professor that taught a class that was dubbed Energy Conversion Design. And this was a required class as part of my ABET accredited engineering curriculum. And it took place in the fall of my senior year at VMI, my first class year. And in that particular class, we spent probably half of that semester, so a whole quarter, on parallel piping system design. And I'm going to touch on that here today. And so many of you submitted questions ahead of time. It seems like hundreds of questions, and a lot of them revolve around a lot of different topics. And definitely, I would be excited to come back to dive into the details. This presentation is going to cover cover 10 topics very quickly. But I'll definitely be happy to answer questions here and stay on, because this is a topic that's important. At IAPMO, we believe in this concept of plumbing resiliency, where you look at most building resiliency, it's about bouncing back from like a hurricane or a tornado or earthquake. And we see, especially like water systems, plumbing systems, it plays a much more integral role. Yes, there's that resiliency of surviving a sudden natural disaster, but things like water, you have water safety, and hot water systems are part of that water safety component. There's also sustainability. I live in Phoenix, Arizona, and we're running out of water here in essence. So we have water stresses in terms of access to sufficient quantities of water. And so that becomes an issue. And then finally, affordability. You can't survive 3 days without water. And hot water systems, it's really this nexus of all those things, because we deal with energy, we deal with the distribution, the use of hot water for bathing purposes, and the safety concern of Legionella. And a lot of the questions that I saw ahead of time, I'm going to try to do my best to get to all of them. But I think a supplemental presentation, if you all are open for that, to dive into some of the weeds, or even staying a little bit after today to hopefully get you going on the right pathway, would definitely welcome that. So just again, very excited to be here, and let's go ahead and dive into it. So to start the presentation, before I go into the top 10, I wanted to spend a moment just making sure we understand the mechanics right. And this goes back to, as I mentioned, my energy conversion class days back in college. And what's been interesting to me in working through the industry, I was fortunate to have a lot of really good mentors during my career. It's just by happenstance in many respects. Folks like Gary Shirazi, Warren Rosenbrook, Carl Couette, Mike Monty. These are folks I had a chance to work with during my entire career, and really have learned so much from them. And much of it kind of goes back to my college curriculum days and taking that theory and the practice and blending it together. So I want to take a moment here to start with that at the start of our presentation, because in order for us to understand and solve hot water return issues, we have to understand the theory behind it to be able to apply it to the practice. So let's go back in time here. Let's go back to school, as it were, and let's just make sure we understand those principles of water distribution and water hydraulics. And so I want to start with, and typically when I give a class on this, either a 1 hour or 2 hour workshop specifically about sizing hot water return systems, I always start with this concept here of parallel pumps, because I think most of us inherently understand what pumps do when they're in parallel or in series. So as you can see here from my two rudimentary diagrams, if you have two pumps in parallel and you have 100 GPM, or 50 GPM, let's say, going through that first pump, the answer's a little bit given away there, but you had 100 GPM or 50 GPM, excuse me, going through, and that first pump was on, and you turn on that second pump. What happens to flow and what happens to head? Well, in parallel piped pumping systems, the flow rate doubles and the head, the pressure increase, stays the same. So if you had a 50 GPM pump with, let's say, make it a unique number, 35 PSI pressure increase, a pump with 35 PSI of head, you would see, as that second pump turned on, you would see 100 GPM and 35 pounds of pressure. because the pipes or the pumps are in parallel. That's the pump affinity laws. Let's go to our bottom diagram. If you had 100, let's say again, 50 GPM or 100 GPM, we'll use 100 GPM and 35-pound pump, and you turn that second pump on, you would see 100 GPM, but you would see 70 PSI on the outlet after that second pump. Because when pumps are in series, you add the pressure, the pressure gains together, but you don't have more flow going through the pipe. As opposed to pumps in parallel, you see that flow increase. And this is why for most booster pump packages, we have the pumps in parallel, because we want to see that staging, that ability to turn up and turn down. So hopefully that concept makes sense. Say not, let me know, happy to go back to that, but that's a key starting spot. So let's switch from pumps to pipes. So if we have two pipes in series, so pipe A, let me see if I can get my laser pointer going here. We have pipe A that is, let's say, half the diameter of pipe B. And we have a given volume of water flowing through both pipe A and pipe B. For the pressure loss of those pipes, you would have the pressure loss of pipe A added to the pressure loss of pipe B. Just like we did for the pumps, the pressure is what changes, but the flow remains constant. Now, flow is impacted by pressure loss, and we'll eventually get to that. But this is one of the key concepts, is when pipes are in series, you're just adding the pressure loss to the different segments of pipe. This is where it gets a little bit more complex. What happens if you put pipe A in parallel with pipe B? So we have a nodal point 1 where the pipes diverge. We have a nodal point 2 where the pipes converge, so the flow of fluids in those pipes converge. And we have pipe segment A that is in parallel to pipe segment B, and pipe B, and apologize for the rudimentary drawing, but pipe segment B has twice the diameter, let's say, of pipe segment A, but the same length. What would happen to your flow and your head? Let's go back to our example of the booster pump. So when the pumps are in parallel, the flow rates increases, right, as you bring them up both up to speed, but the pressure increase stays the same. Similar to that situation here, when you have two pipes in parallel, the head loss across each pipe segment is the same, but the volume changes based on the velocity losses in each one of those pipe segments. Now, I'm not going to dive too far into the velocity equations. I'll touch on it a little bit later. But in essence, there's a velocity squared function that as velocity increases, your pressure loss is a result of the squaring of that velocity. So what that means then is your flow rate through A plus your flow rate through B is your total flow rate. You add those flow rates together, just like you do for the pumps, but your pressure loss through each side is the same. Hopefully you guys are tracking with me on that one. If you need me to come back to that, or if it's in the chat, let me know. But what that means then is, what happens with our flow in each of these pipes? Well, if you looked at the flow rate of A, of pipe segment A, and compared it to B, your flow rate through A, because the pipe diameter of A is half the diameter of B, you would expect the flow rate through A to be less than the flow rate through B, because water is lazy. It takes the path of least resistance. So again, just to make sure we got that concept, the pressure drop from nodal point 1 to nodal point 2, which would be segment A or segment B, they're all the same. But your flow rates, they'll diverge, and they will, when you add the flow rates together, they'll equal the total flow rate coming into and out of this system. Now, if you wanted to get more water flowing through A, there would be several ways you could do this. Normally, when I give this class in person, I ask the audience these questions. So I want you to be thinking about these, but I'm going to go through those answers. Some of the most common ways is, again, remember what I said at the start, segment A is equivalent in length to segment B. So what that means is, if you were to lengthen B, you would have a greater pressure drop per 100 lineal feet And you would expect to see that volume, as the pressure drop due to friction losses in B increased, you would expect that flow rate in B to reduce and some of that water to go to A. Another way you could change the flow rate through B, or to increase the flow rate through A, or excuse me, to change the pipe segment B to have more flow through A, would be by decreasing the size of B. As you decrease the size of pipe segment B, the physical diameter, that more water would flow through A because your pressure drop per 100 lineal feet would increase. The two other ways that a lot of my audience members typically say about increasing the flow through A would be by putting a balancing valve on B, restricting the flow, and thereby creating in your mind, creating an artificial pressure drop in B through that balancing valve, and that would promote more flow through A. Or you could potentially put a pump on A to push that water through. The only worry you would have is at some point you may have some back siphonage and creating a loop where it's circulating, and you'd have backflow in B. So you probably would also need to have a check valve in B, which would also potentially have some pressure loss associated with it as well. So hopefully those things make sense, because that's the basic theory of parallel piping systems. But as we know, in real life, in practice, we don't have just 2 pipes in parallel. We have 4, or in the case of large scale buildings, hundreds of parallel piping systems. And this diagram I'm going to come back to a few times, probably through my presentation, but especially as we're answering questions. But let's imagine we had a recirculating pump down here in the lower right-hand corner with a cold water makeup, and there was a water heater, an expansion tank, and mixing valve, master mixing valve of some kind, all in this location. So that's what this pump symbol here signifies. And the water is circulating in a counterclockwise motion. So we have a loop A, a loop B, a loop C, and a loop D. Each one has one plumbing fixture. Now, in reality, we're going to have hundreds of plumbing fixtures in most buildings, especially in larger buildings. But let's imagine these balancing valves that I have shown here weren't here. What would happen? Well, when you turn on the pump, water is going to take the path of least resistance. And assuming my diagram here is to scale, in essence, you would have water just going through that A loop. You would have no water going to the B, C, or D loops. By adding balancing valves, though, downstream of the last plumbing fixture, we create that artificial pressure drop. And what the balancing valve's job is to do is to create an artificial pressure drop, if you will, in that segment to have the water push out to the next segment. And so again, assuming these are to scale, our most hydraulically remote loop is the D loop, clearly. Although sometimes in certain buildings, the loop that goes the furthest is not the most hydraulically remote, because pipe size impacts hydraulic remoteness as well as length. But for the cases of this example, it is the most hydraulically remote. And so this balancing valve will have a greater pressure drop across it. You'll have it be closer to being closed than this one. And C will be even less than B. And then you have your D loop, which has probably the least, will be the most open, the least closed balancing valve, because it'll allow the most amount of water and it will require the least amount of pressure, because again, that water is going to take the path of least resistance. So that's the concept of fluid dynamics. Now, I often get asked in some of the coursework that I give, do you need this D loop? And technically speaking, you don't. The system could be controlled just by having an A, B, and C balancing valve. However, in practice, it is a good idea to have that D loop, because it gives you just that a little bit more of added control, especially in the event of, let's say you added an E loop somewhere outside of that D loop and connected it at C3, not upstream of C3. That would create a balancing issue. You don't want balancing valves in series. They always should be in parallel. But now you wouldn't have to install a balancing valve in the D loop, because your E loop now would be the most hydraulically remote. So your most hydraulically remote doesn't require a balancing valve. But again, in the field, you don't know how it's going to be constructed. So it's always a good idea to give yourself maximum control. Also, facilities like healthcare facilities and others that undergo renovation, you're going to want that additional added level of control. All right, so that's the whole theory of things. And we just spent the first few minutes on that. So let's go into some of the top 10 things here. So first off, we need to start with definitions, because we always need to make sure we're using the right definitions when we're talking about whatever it is that we're talking about. These two definitions come from the ASPE engineering methodologies to reduce the risk of Legionella in premise plumbing systems guidance document or design guide that was just recently released at the start of this year. This document is for purchase on the ASPE website, and I'm going to refer to it a lot because this is, as far as I'm aware, one of the few, if not the only document that really delves into the depths of, and I should say third-party guidance documents that delves into the depths of hot water and hot water return systems and how to do it. So again, if you have questions or you want to dive into the details, I would definitely refer you to that document. I'm going to refer to it a few times here in my presentation. The most critical definitions, and this was ones that was agreed to by the group, was recirculation versus circulation. And I'm going to refer to these definitions and use these definitions moving forward in my presentation and outside of my presentation too. So we often conflate circulation with recirculation, but what the Legionella Task Group, the ASPE Legionella Task Group decided on was circulation was the movement or flow of water between a boiler and some kind of hot water generator and an associated storage tank. So oftentimes tank top water heaters have them integrated. You don't have a separate circulating pump, but oftentimes, especially for larger buildings, you might have those separated. So any water flowing between a hot water generating source and a storage tank, that is being controlled by a circulation pump. A recirculation pump, that definition, even though technically the word recirculation does not technically exist, we did make note of that in the definition. And a gentleman by the name of David Dexter was really poignant in some of his points on that creation. But we wanted to create this definition because for us, recirculation indicated from that hot water from that mechanical room distributing out to the system. What was that system was called the recirculation system. And getting it out into the facility, that definition we felt is really important to make that delineation, because the rules for circulation pumps versus recirculation pumps and the things you want to do and how those systems are sized and all the corresponding information was very different. And we wanted to delineate that difference in part of this document. So again, recirculation is what's going out to your building. Circulation is what's happening in your mechanical room between your storage tank and your hot water generators. And with that brings us to our first poll question. Mary, did you want me to read the poll question, or were you guys going to read it? I'm happy to go either way.
Goodness, I guess we didn't practice that, but please go ahead and read, and then we will share with you the results. You may read.
I'm actually really curious about this. So for what recirculating pump do you typically specify for recirculation systems? So again, remembering that when we talk about recirculation, this is out from your water heater source to the building, not to the storage tank. So I'm definitely excited to see what everybody comes back with.
Okay, we'll give that just a few more seconds here.
Oh, these results are fascinating. I'm watching the poll right now.
Okay, good. Okay, I think we can close that poll and display those results. So
Perfect.
would this be what you would have anticipated, Christoph? It looks like.
I think so. I think I would have probably anticipated fixed speed being a little bit higher. So I think, can everybody see the poll? Is it displaying? I don't see it on mine. So excellent. So fixed speed comes in at 36%, followed by constant temperature at 28%, and then constant delta P at 20%. And we have a few others that don't know. And I would say that would be the fixed speed was probably going to be always the one that was the highest. It's interesting to see as many people voted constant temperature. And I think this is that especially that change to utilizing thermostatic balancing valves, which we're going to touch on here in a little bit. Some very exciting developments in that realm. But yes, fixed speed, I think there's still a large part of the market that's using that from the design perspective. And constant temperature, I think, has made a lot of inroads. Constant change in pressure, constant delta P, that's an interesting one. And I wouldn't have expected that one to be so high. So you always learn something on these. And so I'm very interested to hear questions and whatnot as we move forward here. All right, so moving on to the next slide. So we talk on the pump types, but and we'll come back to that topic here in a little bit. But let's touch on balancing valves because we've been focusing on that. So part of the ASPE engineering methodologies document, I'm not going to say the whole name. Maybe we can put the link in the chat. It's out to the ASPE bookstore. But we did a designation between two main types of valves. So we had automatic balancing valves and manual balancing valves. Now, manual balancing valves are the type that probably have been used most consistently in industry. I think that's the most prevalent type. That's the one I started using over a decade ago now, when I started doing hot water return system design. And those valves, often with the Kleenex branding of circuit setter, those are the valves that have that knob on the side with CV values. And they started being used prevalently in hydronic systems, systems that heat and cool the building. And that's really where the start came from. And then they made them low lead for the domestic water system. Those valves with that CV value on the side, there's a calculation that gets associated with that. And if I remember right, it is basically that GPM equals the square CV times the square root of the delta P. Hopefully I didn't goof that one up. I always have a hard time remembering that equation. But in essence, you're changing your CV value to get an artificial pressure drop across the valve to hit a target GPM. Those valves require a test and balancer to come into the building and balance those valves. Now, when I've asked the question for a lot of engineers out there across the country, and I've probably given a version of this hot water return presentation or talked on hot water return systems, hundreds of times, so spoken with thousands of engineers. I asked the question, how many of you have testing and balancing requirements in your specs? And all the hands go up. And then I ask, how many of you get test and balance reports on a regular basis? And all the hands go down. Even though it's in the specs, even though it's a requirement, it's a problem that we all have had. And I'll raise my hand there too. I've had it in my specs, and very rarely on a project do I get that test and balance report. So what I have sensed in the industry, and some of that changed when I started working for some of those great mentors that I mentioned earlier, the valves that we've switched to is automatic balancing valves. And the way that the ASPE Legionella Task Group designated automatic balancing valves was those valves that didn't require a test and balancer to come in. Now, you still might want commissioning, right? A validation of some kind that the valves are working as intended. But the valves themselves didn't require somebody coming in and necessarily having to go through and test and balance the whole system, maybe just an adjustment of the knob. And we created 3 subtypes of automatic balancing valves. So we have pressure independent balancing valves, thermostatic balancing valves, and electronically actuated balancing valves. So the first one, pressure independent balancing valves, these are ones that will create an artificial pressure drop across the valve that will maintain a given flow rate through that valve. And there's cartridge, fixed types, or adjustable type. Thermostatic balancing valves will modulate that flow rate and pressure drop through the valve to maintain a given temperature. And those are fixed cartridge or adjustable type. And last but not least, we have electronically actuated balancing valves, which can do either pressure independent or thermostatic balancing valves or other means of controls. And so these 3 types, pressure independent, thermostatic, and electronically actuated, were all considered by our group as automatic balancing valves. And we have those delineations in there. And the general rule with these ones was you don't need the test and balancer, but probably some commissioning. And you achieve a higher end level control of the system, because when you use a manual balancing valve and you make a modification to the system, the entire system needs to go back and be rebalanced. And that was one of the big negatives of the manual balancing valves that we saw. Now, if your building doesn't change, no problems, but in a hospital, it doesn't. And one of the other things we noticed is that, especially from the engineering perspective, we tend to define our scope very narrowly when we do renovation projects. And I'll raise my hand. That was a large part of my career. I wish I could go back in time and go back and ask for rebalances of systems when I used a manual balancing valve. But much of our industry, especially for new buildings, we've seemed to go on with the automatic balancing valve, at least from my perspective. And that's why IAPMO and ASSE, we created an IGC standard 368 for thermostatic balancing valves. This will be the C document for a new IAPMO ASSE ANSI standard 1115 2020 something. We'll have to see when that ASSE standard comes out. But that will become a new automatic balancing valve. So that thermostatic balancing valve standard will be the C document for the automatic balancing valves. And we are already in process of getting at least one manufacturer certified to that. And I imagine there'll be more to thermostatic balancing valves. So very exciting to see this take root, because we really haven't had any kind of literature or code requirements when it comes to balancing hot water return systems. So this is really a first great step that we see in this regard. All right, so for our next poll question, I'm really excited about this one, I have to say. We have, what types of balancing valves do you typically specify in recirculation systems? Manual, pressure independent, thermal, other, or NA, or do not know? So if you want to open up that poll, I'm really excited to see these results here.
Yep. Us too, Christoph, if I can say. And gosh, I'm still back in the water is lazy. Recirculation doesn't really technically exist. So I'm sure your audience is swimming with lots of information. And Cody Mack has joined us. So Cody, thank you for joining us.
Yeah, hey, sorry for being a little bit late to the party here, but yeah, it looks like the poll question is actually getting a lot of answers here. And while we're waiting, Christoph, thanks for your time here today and everything like that too. And I look forward to seeing these numbers just as much as you guys do, that's for sure. So looks like we're almost at 3/4. I don't know if we want to shut this poll down then, Mary, or
Yep, I think so. What do we got?
quite a surprise there, to be honest with you. I don't know about you, Christoph.
You know, I try not to be surprised, but it's interesting, the results, because what I see is manual is still on a very high end, but the market, which I think was my sense, are largely going towards pressure independent, but thermal has made a really big inroads in the market, and that is a really interesting result. So, but not entirely surprising, I would say, because I think ultimately those thermal balancing valves, they help solve a lot of problems. And ultimately, and at the end of the game, you know, whether it's Khalifi, IAPMO, or any of our engineers or plumbing design professionals that are on the call, we're all in the business about trying to solve problems. And I think a large problem that has been out there has been domestic hot water return systems. And I think the balancing side has been a big challenge. And so automating that, simplifying that, you know, to see that, you know, two automatic types of valves, pressure independent and thermal, have made big inroads, it's not surprising. I think electronic is still on the early side. That said, I think especially because of my personal prediction is in the next 10 years, I think because of ASHRAE 188 and some of the requirements, especially now that it's been CMS, and if you're doing healthcare work, I think we're going to see more inroads in that market because of the ability to data collect too. And especially when it comes to litigation from waterborne pathogens, this concern of documenting everything so you have it in a court of law, I could see more inroads there. But for right now, you know, it's interesting to see that the shift in the industry, because manual used to be basically the way to do it. I think it was about 100% manual or pretty close too. So the last 10 years to see this kind of shift where automatic balancing valves have made significant inroads, it kind of jives with some of what I've seen. But thermal, that's amazing. But I think that's also a reflection of how the industry is kind of going and trying to make, you know, problem solving streamlined. So not entirely surprising, but amazing to see nonetheless. All right, so moving on to our next top 10 item is a new standard for digital master mixing valves. Now, most of you are probably aware of master mixing valves, ASSE 1017, and there's really no code requirement that requires the use of 1017 valves in any building. However, many people will still use them, and for good reason, just to have that additional level of control in the central plant, especially if you have two different hot water lines. Let's say, you know, a 160 line going to a laundry facility, and then you have 120, let's say, which for many years is what people done. I think now people use 160 and 140. Would be interesting to know what temperatures you all are using. But the challenge came up that with ASSE 1017 is that the valves in there had some specific performance criteria that digital master mixing valves that have really come onto the market within the last 10 years are trying to address other problems that 1017 wasn't specifically targeted for. And so a really good article in Working Pressure magazine appeared. I have the QR code for that one called Raising the Standard, that talked about the need for digital water temperatures. So I would definitely recommend you guys go to Working Pressure and become a subscriber. I believe it's a free download. And that led to the creation of an IGC, another IGC standard 384, which will be the seed document for an IAPMO ASSE ANSI 1118 2020 document for digital master mixing valves for recirculating hot water systems. And so this is one to keep an eye on as well, because master mixing valves have some, especially on the mechanical side, have some challenges when it comes to being able to stay on continuously and temperature creep. And this standard here, this digital mixing valves for recirculating hot water systems, the testing protocols are specifically there to show the ability for a valve to be able to avoid temperature creep, to maintain constant flow in a hot water return system. So this is another one that's worth looking at. And I have the QR code to go to the APMO ASSE bookstore to view it for free online, or you can purchase as well. All right, so when I was looking at the list of questions, the questions you all submitted, a lot of questions came up on right sizing of hot water supply systems. So to start with, in order to size a hot water return system, the first key point is sizing your supply system. Now, we still are under the Hunter's curve for most of the US and most of the world. However, back in the 2018 Uniform Plumbing Code, which IAPMO released, the water demand calculator, which is the first time in 80 years that right sizing of supply systems was evaluated, that particular sizing tool was released. It's a free download on the IAPMO webpage. I should have put the QR code up there, so my apologies for that. But if you Google IAPMO water demand calculator, it'll take you right to that page, and there's a free download for version 2.2. We looked at empirical data for residential buildings, so single family or multifamily. And we're able to basically see that instead of sizing a building like a sports stadium at halftime, which is what the Hunter's curve assumes, that kind of congested flow rate, we looked at real world data and realized that we could go much smaller. We had better probability values or P values. Now, when you look at Hunter's curve, the question often comes up, oh, well, we adjusted for flow rates, and more flow efficient fixtures. That's just the Q value, the flow rate through the fixture. But the fixture unit is a value of probability and flow rate. So the probability of that fixture being on at the same time as other fixtures. And if you don't go back and evaluate the P value, no pun intended in terms of the plumbing systems and P value, but the probability value, you're really only going to see marginal savings because you're still assuming congested use in the building. By looking at real world data, we were able to much more accurately size peak flow rates in the building. And again, for multifamily, we see some pretty big increases. As an example here from an ARAP report that we just published on that webpage, which you can download for free, along with the calculator itself, we saw significant heat loss and water savings by right sizing with the water demand calculator. So as opposed to Hunter's curve, which is just kind of represented there by the purple line. So when you look at the potential savings of right sizing your supply lines, there is an impact on the return side and energy usage because the larger the pipe is, the greater the surface area, the more heat loss you're going to have through the pipe. And there was a lot of questions. I think about half the questions that came up that I saw sort of in prepping for the presentation here, as I was going through with my highlighter and highlighting everything, dealt with this question of how do we size hot water return systems? Now, when I go to the ASPE symposium, I have a presentation that's going to deal with for over an hour on this subject. And I would love to come back. And I think Kalefi and I, we had these conversations that I think I'll be coming back to do a presentation on this post ASPE technical symposium just on this topic. I've given this presentation across the country. Always have a lot of questions on this one. But I'll give you a brief overview here just so that to definitely give you guys pointed in the right direction. So the whole methodology, it covers Hardy-Cross methodology, is located in that ASPE General Design Guide. Again, it's a third-party design guide that you can purchase from the ASPE website. So highly recommend that. Worth noting, I guess disclaimer, I was the chair of that task group for the last 3 years through COVID, but was really excited when we were able to release that here at the start of this year. As I was saying, in terms of right sizing hot water return systems, we have to remember what the whole point of hot water return systems are. In essence, when you look at any of the codes, energy or plumbing codes, the intent is to bring that hot water source as close to the fixture as possible. Because if you had a 100-unit apartment complex and you had your water heater and just a hot water supply, and you were on the top floor and you turn, let's say your water heaters are on your top floor and you were in one of the lower floors, because typically for high rise we put the water heaters up top. But you turn on your faucet in the lower floors, you'd have to wait for that entire length of hot water that has cooled off overnight to be displaced by hot water from the water heater. That is why we recirculate the system. We have a return system as part of that recirculation system, is to have that hot water flowing and bring that hot water source closer to the fixture. So that way you may only have to wait, ideally, a few seconds. In reality, in practice, often it's a few minutes because of balancing issues, which we can go back and touch on. But the key point in this is, so when you look at the literature that has been out there for much of the last 50 years, often we just use this. There's one of these methods that say just use 30 BTU per hour per lineal foot and assume that for all of your piping. The problem is when you actually calculate out the numbers based on energy code insulation thicknesses or plumbing code insulation thicknesses, and you look at various insulation, different pipe sizes and fluid temperatures, you will end up with different BTU per hour per foot heat losses. So again, that old school mentality was using 30 BTU per hour per lineal foot. You don't reach that with a 2-inch thick insulation pipe until you hit either a 4-inch pipe at 160 degrees Fahrenheit or a 6-inch pipe at 140 degrees Fahrenheit. Now, hot water systems, especially if you're right sizing, more often than not, in my experience, have been, especially even for like a large hospital, are 4 inches and less. And especially for smaller facilities with water demand calculator, you can get 2-inch, 1.5 inches or less, depending on the size of your facility. So a lot of our piping tends to be 3/4 and 1/2 inch, especially on our return side. And so if you're assuming 30 BTU per hour per lineal foot, your pump size is going to become grossly oversized, which could potentially also be a contributing factor to temperature creep, especially if your pump is going too fast for the system and bringing back more water than the system can handle. So we have all these unintended consequences. So the first step is using Hardy-Cross methodology and is assuming, or it is utilizing as close to possible as the correct BTU per hour per lineal foot loss. Now these tables, again, are right in that ASPE Legionella design guide. And there are some assumptions with this though that might be worth going back and reevaluating. For instance, the ambient air temperature to determine these BTU losses was 65 degrees Fahrenheit in the plenum space. I live in Arizona. A lot of times in the summertime, our plenum spaces are not 65 degrees Fahrenheit. They're much hotter than that. So your heat loss transfers, these numbers would likely go down even further because you're not going to have as great of a temperature difference. It's also making some assumptions about this being type copper piping. Could be using a different material, which has a different piping material, which has a different K factor or conductance factor. But we started with this, again, this was a step in the right direction. And even the ASPE heating guide, which is a wonderful document, which has a simplified table for 120 degrees Fahrenheit, we thought these tables were much more accurate representation that would include different fluid temperatures, because I think most of us are probably dealing with different fluid temperatures now in different building types. I'm hearing a lot more healthcare facilities are going with 140, 150, and 160. Hospitality has increased from 120 to 130 to 140, and with many of the engineers I've talked to, they're bumping up that temperature because of waterborne pathogens concerns. So again, that first step in right-sizing hot water return systems is getting the right BTU per lineal foot loss, and not just assuming a blanket 30 BTU loss. So that's another one of our top 10s. But let's focus on this Hardy-Cross methodology. If you were to go in the Michael Lindberg Mechanical Engineering Reference Guide, the one that I used to prepare to take my PE over a decade ago now, which is kind of crazy to think about, it describes the Hardy-Cross method. And remember, I talked about that class, energy conversion design, early in the presentation. This was the methodology I spent a whole half of a semester learning and putting into MathCAD and understanding the dynamics. As I've talked to engineers, degreed engineers and PEs, there seems to have been a gap somewhere after when I went to college. Sometime after that, engineering, ABET accredited engineering schools dropped this class from the required curriculum. And so we have a whole generation, from my perspective, that seems to not understand parallel piping systems. And so going back and learning what Hardy-Cross methodology is vital. To quote Michael Lindberg here, network flows in a multi-loop system cannot be determined by any closed form equation. The reason for that is you have too many equations and not, or too many variables and not enough equations. You have one more variable than you do equations to try to solve via closed form equations. So most real world problems involving multi-loop systems are analyzed on a computer. Computer programs are based on the Hardy-Cross method, which can also be performed manually when there are only a few loops. And this is the method that basically I learned working under, or relearned, I should say, working under Warren Rosenbrook. In this method, flows in all of the branches are first assumed, and adjustments are made in consecutive iterations to the assumed flow. So what does that mean? So what that means is there's a series of, I believe it's about 4 equations. You can make an argument that's 5. There's 3 or 4 equations or 4 or 5 variables. But one of the consistent variables is flow rate, because it impacts velocity, and it also impacts the delta T based on your BTU loss equaling 500 times delta T times your GPM. So if you assume a flow rate during closed state condition for your hot water supply and return system, so no plumbing fixtures are open, that's how you start this, you can do a iteration and determine what your heat losses are, what your temperature losses are, what your velocities are in each of those pipe segments, and you can make sure that all that jives. But then what you go back and do is you say, I'm going to do another iteration. I'm going to change that flow rate variable. and go back and recalculate what all those losses are and see which, and you can keep iterating like that over and over again until you get to a pretty close answer. The problem is Hardy-Cross methodology has not, to my knowledge, I'm not aware of a program for domestic water systems that deal with it. On the hydronic side, it actually is very easy because you tend to have less parallel branches than you do on the domestic water side. But if there's somebody that has a program out there, I'd be interested in learning more about it and seeing what's out there. But this Hardy-Cross methodology and that continual iteration and getting closer to the answer that you want in terms of your target delta T, your target velocities, and all the rest, this is the method to do. And it's been out there. It's just nobody seems it seems we've forgotten about it as an industry. And so this is one of the ones, again, I would point you to that ASPE General Design Guide. There's an appendix in the back that deals exclusively with how to do this methodology and what that process is. So definitely this is one of the ones that in terms of developing that flow rate and creating the calculations, this is what should be used. And that is very well detailed in the ASPE General Design Guide.
Hey, Christoph, we had a quick question too that was asking about the charts for the insulation thicknesses and the pipe sizes and stuff like that. That was in the ASPE Regional Design Guide as well, right?
The ASPE Legionella Design Guide, yes.
Legionella Design Guide.
Yes, so it's the official document title is ASPE's Engineering Methodologies to Reduce the Risk of Legionella in Premise Plumbing Systems. I'm sorry we picked the longest name, but we tried to make it descriptive. I usually refer to it as the ASPE Legionella Design Guide for short.
Perfect. Thank you, Christoph.
And that is a design guide. No problem. All right, so another top 10 for something for all of us to kind of keep an eye on is credentialing and licensing. Especially when it comes to Legionella, my sense is that we're going to see an influx here of the need to having the right credentials and licenses for domestic hot water systems. And it comes through a few facets here. So the first is an effort that I've been involved with now for probably about 5 years, predating the COVID pandemic, which includes the creation of a professional engineering exam under the mechanical discipline for plumbing. When I took my PE, again, about 10 years ago plus now, I had to take an exam in HVAC and refrigeration. And the only options are, still to this day, include HVAC refrigeration, solid mechanics, and thermal fluids. Thermal fluids didn't really deal enough with what I was doing on a day-to-day basis, although I know some engineers did take that. And so a lot of plumbing engineers, or that is mechanical engineers that focus on plumbing systems as opposed to HVAC engineers, which are mechanical engineers that focus on HVAC, had to take that HVAC and refrigeration exam. As part of the last 5 years, I've been part of ASPE's professional engineering working group, working with David Dexter and Ron Ensley. And we have had a lot of great success. We were able to get 10 state licensing boards, especially a number of them during the COVID pandemic when a lot of meetings went virtual. And we were able to get to the next step with NCES to begin the creation of at least of an outline for the plumbing engineering exam under that mechanical discipline. So this wouldn't be like a fire protection engineering exam, which is a completely different discipline. This is under the mechanical discipline specifically for plumbing engineering. So there'd be a morning and afternoon portion that would cover topics in mechanical engineering as it relates to plumbing. Now, what I'm very excited about with this is it highlights the need to have licensure for plumbing engineers, which has been not the case for a number of years. And if you follow me on LinkedIn or follow my articles in PM Engineer Magazine, my column, I focus on this topic a lot. It is so important for plumbing engineers to have a pathway to get licensure, especially because some of these theoretical conversations on Hardy-Cross, we need to have people that have a really good understanding of that. And that's not to say that design professionals, that is non-degreed and non-licensed designers, don't have the ability to do it, but it's about creating an ecosystem where more of us have that understanding. And so all of us need that, but having that pathway in college coursework to bring that into the plumbing and having a path for licensure is a really important step in getting our best and brightest into this realm of plumbing to solve these problems that we're seeing in hot water systems like hot water return systems. But it also extends into credentials outside of licensure. A really good one is ASSE 12,000 series, specifically 12,080, which is a Legionella risk mitigation specialist. That's one of my letters in my alphabet soup after my name, which is a really great class that touches on the nexus between waterborne pathogens, and infection prevention control. That class, from a plumbing standpoint, was very, very basic, but from waterborne pathogens and testing and understanding infection control risk assessments, that document is a really wonderful one. There's other ones out there, 12,061, which is for the plumbing installer. and there's a few others in there for other licensure as well. All of these are credentials, and if you go to that ASPE Legionella Design Guide document, it lists out these credentials and even gives recommendations, and perhaps for an engineer to consider, to require a 12061 plumbing specific credential, plumbing installer specific credential, to have somebody with that credential on doing the work on the site. In many respects, it mimics a lot of stuff we've done on medical gas systems, the ASSE 6000 series, which has an installer, verifier, inspector, maintenance person, and recently added a 6060 for the design professional. These kind of credentials, especially for non-degreed engineers, it's going to become a really vital part in making sure our hot water return systems are being designed to the best ability and being installed and maintained to the best ability. So my sense is there's definitely some discussion now on, should we have inspection and verifications for hot water return systems like we do for medical gas? So that's going to be something for all of us to kind of keep an eye on moving forward. And that kind of gets to my next point, which is the testing and balancing or commissioning of hot water return systems. This is going to become a very hot topic in the near future. This is something that we're going to need to spend a lot more time on focusing. And I want to share a quick story here. We're kind of coming up towards the end of my presentation, just a few more slides to go. But there was a large hospital, multi-story hospital, with a great water management team that won an award for being the best Legionella risk mitigation group out there. They won an award for their water management program. They had a contractor working on a new project that was reputable. The engineer understood Legionella systems. They even added supplemental disinfection and had higher hot water return temperatures to try to do everything they could to mitigate Legionella. Unfortunately, they had consistent outbreaks and positivity in one of their loops, in one of their remote loops, going to one of their sinks, and it was a staff sink. They were trying to figure out why. Part of the problem was the testing and balancing and commissioning of the building. That loop was basically an operational dead leg because that balancing valve was almost entirely closed off. It was a manual balancing valve. And so there was no flow when that sink wasn't in use. There was no flow through that loop. And so recolonization happened over and over and over again. So the only solution was, for a long while, was to flush that water down the drain until the problem was rectified by changing out the balancing valve and rebalancing the system. So balancing has a profound impact on waterborne pathogens because if it is done incorrectly, it can lead to stagnant water conditions, inadvertently, but still nonetheless stagnant water conditions. Another item for you all to be aware of is ASPE's new standard on thermal disinfection systems, ASPE 99. This is a document. I'm involved in the committee on this one. It's talking about the implementation and management of thermal disinfection processes in domestic hot water systems. This one's currently in process. I think we're still maybe a little while away before that one gets issued, but it's going to cover additional topics, and I think it'll be a nice package to go along with that ASPE engineering methodologies for Legionella design guide as well. But this will be an ANSI standard that will be part of the process here. So this is one to keep an eye on moving forward. All right, now one of the last top 10, I think this is my last one here, just with some follow-up slides here, is talking about hot water return pumps. Now, one of the questions I saw that came up in the list as I was looking through it was this question of, well, how do we control the pump or what do we do with the pump to maintain, flow? And a lot of you asked questions about C404.6.1 in the energy code. When you look at C404.6.1, circulation systems, although they mean recirculation systems, so this is, again, the definition in the ASPE Legionella Design Guide doesn't necessarily correlate with the definition here, but the heated water circulation system here is, in essence, describing a recirculation system. It says the controls shall automatically turn off the pump when the water in the circulation loop is at the desired temperature and when there's not a demand for hot water. Now, this has caused a lot of consternation and a lot of frustration and potentially some issues in facilities that are susceptible to waterborne pathogens such as Legionella pneumophila. And if you look at Act 188 and you look at the litigation of Legionnaire's disease, we're talking predominantly of healthcare facilities and then followed by hospitality, which is the second most litigious building type when it comes to Legionnaire's disease. But looking at healthcare facilities, there's been a lot of engineers that have been having challenges with plan reviewers in regards of not wanting to turn off the hot water return pump when the demand is not there in a hospital. Why is that? So let's say you had an aquaset on a hospital and your hot water loop was running and you shut it off. Your whole loop that's not circulating or recirculating anymore, I'm sure I'm using the right terminology here, not getting it mixed up, part of that will cool off. That section that's not flowing will cool off. Then let's say you turn the pump back on, when the sensor back at the pump is there. That water is going to continue to flow or start flowing again, and your closest loops are going to start seeing that temperature increase. Now, depending on what's happening with your system, if and where flow is going to, you may see that coldest loop, that furthest, most hydraulically remote loop, may not ever get back up to that temperature to basically be in that design temperature range, let's say. And it stays permanently in a tepid or tempered system, basically between, let's say, 90 to 120 degrees. Well, unfortunately, that's a growth range for waterborne pathogens, especially Legionella pneumophila, which we know loves about 100 degrees Fahrenheit plus or minus 20 degrees Fahrenheit. And now, in essence, you created a situation by shutting on and off that recirculation pump to try to either meet code or to try to work to prevent temperature creep, of having a location where that pathogen is growing, because in essence you have a slug of water that's not getting moved, especially if the system is unbalanced. So we've compounded an issue by trying to solve another issue, and that's where plumbing resiliency really comes in. You have to think through problems holistically. With that, though, when you have that slug of water that's not ever getting heated back up, and that growth of waterborne pathogens, we had a lot of engineers that have recognized this. A lot of plumbing design professionals have recognized this and have been fighting with either energy inspectors or energy plan reviewers or energy authority having jurisdiction to let them run the pump continuously. There was actually one example that I was aware of an engineer going so far as to put an override on the aquastat, or putting a sign on the aquastat and putting a switch on the aquastat that says, leave the switch on, because the switch overrode the aquastat turning the pump on or off. We also have new technologies in place. Again, I mentioned the digital mixing valves. We have these balancing valves now that do a better job of balancing, the automatic balancing valves. They help solve some of these issues, which is why we're starting to see the market go that way. So do we need to turn off the pump anymore? Now, you could argue, well, there's a lot of energy wasted, but if you size your system, you go back to the right sizing that I touched on, by right sizing your plumbing system, in theory, we should be able to get a system where the flow of the water through each of those parallel branches displaces exactly 100% of the heat lost to the space. And if we are displacing 100% of the flow exactly, there should never be a need to turn off the circulation loop, or the recirculation loop, excuse me. Not only that, but in healthcare facilities, some supplemental disinfection devices require, for them to operate properly, to be on continuously. Otherwise, they can't achieve control at lower temperatures or at higher temperatures or whatever temperatures. So getting the hot water return loop operating in the right way through design, installation, construction, and operation is vital. And that is why in the 2024 Uniform Plumbing Code, which was released at the beginning of this year, a new provision was added into Chapter 6 of the UPC, along with Appendix L, which appendices have to be adopted, opt-in by jurisdictions to be considered part of code, but it's an opt-in provision. And in Chapter 6, they added this line down here in red. For healthcare facilities, long-term care facilities, hotels, or motels, devices that automatically turn off the recirculation pump or pumps shall not be required. And this exemption basically allows you in UPC adopting jurisdictions, I will adopt the 2024 UPC, to supersede the requirement to turn off that hot water recirculation pump. And it will allow you to run it continuously. Now, you still have to be mindful of the design, still have to have control, not try to find a way to deal with temperature creep, but that's all design criteria. This is one of those instances where the codes may not correlate, but this is one of those provisions that the technical committee ended up adding because they saw it as a public health and safety issue, not as an energy issue. So it's going to be very interesting to see how this moves forward, but at least this gives the design professional that mechanism to say, look, code gives me this allowance for these building types. Keep an eye on this one. My sense is that this whole topic of hot water return systems and codes and standards, it's only going to grow in the next few years. So it's definitely one to keep an eye on. And on that note, I wanted to make sure to link to the IAPMO and ASSE standards newsletter. This is a great way for you to stay in the know on what's happening in new codes and standards development. The QR code is right there. I would highly recommend that one. I subscribe to it as well, so I'm walking the walk here and walking the talk, as it were. And I think it's also, all of these things I'm touching on is really a great example of why plumbing expertise matters for innovation. One of my favorite authors, Peter Drucker, the founder of modern management, in his book On Management from 1974, has this great quote that talks about brain surgeons, versus general practitioners and specialized knowledge. And he said, and this end part of the quote is a really vital one. Because knowledge rapidly deteriorates unless it is used constantly, maintaining within an organization, and I would even argue within an individual, an activity that is used only intermittently guarantees incompetence. And I think this is one of those key quotes that we should really keep close to the vest, because it really makes us as engineers, really should make us think, what am I specialized in? What do I really understand? What are my limits? And I think for a long time, we haven't thought about hot water return systems as a specialized system. But I can tell you, after having done hundreds of designs of hot water return systems, especially ones that followed Hardy-Cross methodology and good sizing practitioners, it is a complex system. It's one that we can solve, but it is a complex system. And it does take specialized knowledge to really understand it. And kudos to all of you being on this call here today. One of the things I want to encourage you on as kind of a departing note is strategic design thinking. So what do I mean by this? I got a few pictures up there of a famous Colonel John Boyd and Mr. Oppenheimer. I would highly recommend that movie in terms of any technical professional. I saw that really wonderfully done movie. But oftentimes, especially here in the US, we tend to think in terms of task. And I'll raise my hand as an engineer. I was trained here as an engineer. I tended to go task to task to task. And I didn't consider how those tasks interrelated. One of the things that we have to realize is that we can't just call one play, that we're dealing with a much larger system, an ecosystem. And we always, even when we're completing very detailed work, we always want to make sure we take the step back and look at large picture and not lose the forest for the trees. How does each of these components that I pick and that I select and I specify and design around, how do they interrelate? What is the impact on the system? Thinking from a sports analogy, football tends to be very task focused. It's very much a sport of, the coach calling the plays, running back going through a line, or the quarterback, looking a certain way and selecting one of a couple options. Soccer, on the other hand, which is my favorite sport, for those of you that can't tell, it's much more of a systems-based game. The coach has very little to no control over his players, but they try to implement a system that his players will work around and make constants, hundreds, if not thousands, if not millions of decisions on the field every second in terms of implementing that system. And if you look at American football, it's even gone more of a systems-based approach. Look at the spread offense. Look at those opportunities to make a decision and giving the quarterback and others on the field, wide receivers and running backs, more opportunities to make decisions on the field to confuse their opponents. We're getting into a systems thinking world. And for hot water return systems, it's a system, and we need to think of it as a system. So with that, that concludes my presentation. There's my contact information and my QR code to connect with me on LinkedIn and my bio. Just want to say thank you and happy to entertain any questions at this time, if we have
Perfect. Mary, do you want to go through the ending slides, or do you want me to?
Yeah, why don't I do that just quickly? I want to say, Christoph, thank you so much. I think the one common thread that unites all of us is that we have a love to learn. We really, really do. And at the beginning of the presentation, we talked about hydronics. I will offer to the audience in a post email just a couple of additions of hydronics that really came to mind to me as you were talking. But one of them was safe and sanitary hot water delivery systems. The second one, recirculating domestic hot water systems. So we'll make sure that we offer that out. Just a couple of closing notes here. Our technical support team are good-looking guys at the phone, answering it and helping in terms of answering some of these technical questions. I know these systems get complicated, but they are there to help. So to answer questions and solve problems that folks and contractors, installers, et cetera, see in the field. We also have a podcast series, a lot of fun just listening in. If you've got some drive time, please tune into the Ask Calefi podcast. I think you will be quite enjoyable with that. And the next slide. Okay, we're on social media channels. I think predominantly all of those are super cool, but YouTube, we mentioned at the beginning of the webinar, we do record these webinars and post them up on YouTube. There's so many resources on YouTube, it's crazy like. So make sure you check us out, follow us, etc. So Cody, with that in mind, I would like to pass the baton back to you. And if folks are still interested in a couple of questions and answers, now's the time.
Perfect. Yeah. So I was just keeping track of a lot of questions here, and there was quite a few of them. And I will say there was a lot of pre-submitted questions. Christoph, you saw them. There was a lot. And it's going to take us a little while to get back to everybody, but we will definitely get back to everybody. But while we were here today, there were a lot of questions, some easy ones and some that are not so easy. And if you feel like hanging on, there's a lot of you hanging on here. We want to make sure we can get to these. I think they'll benefit everybody. So the water demand calculator, that was a question that got brought up. Was that adopted into UPC? I'm pretty sure it was referred to as Appendix M in UPC.
Yes.
Is that correct?
Yes.
What year was that?
So the water demand calculator was part of the 2018 Uniform Plumbing Code. And it's been in there for 2021. It's in the 2024. And it's actually very exciting. We're working on the commercial sizing now too. So we've made a lot of inroads. So stay tuned. There's definitely a lot of excitement in terms of commercial buildings. So healthcare, offices, schools, those types of buildings. So outside the residential market. But that was in the 2018, UPC.
Yep.
Worth noting, since it's go ahead.
No, go ahead. You finish up.
So worth noting is that since it's an Appendix M, it has to be opted into jurisdiction. So places like Nevada, New Mexico, I believe.
State of Wisconsin has it allowed now too.
That was pretty exciting. State of Wisconsin, which is under the Wisconsin Administrative Plumbing Code, they're their own plumbing code. They just adopted it last year in July.
Yep.
We also have New Jersey now. The NSPC just added it this last code cycle. So that's now adopted in New Jersey. But a lot of projects from California. California's adopting it next year. They just did an interim code cycle adjustment, so that'll be coming out in 2024. But even in places like New York, we have a lot of engineers that have used it and just gotten a modification from the AHJ. They've worked with their AHJs. But if you're interested in getting it adopted in your jurisdiction, please reach out, because we're definitely looking to work with folks to get it adopted. And we've gotten it adopted in a lot of locations, and a lot of excitement has been generated around that, especially because of the energy, water, construction cost savings, water quality impact, positive water quality impact by reducing water age. So yes, but it's been in there since the 2018. Also in the IAPMO WE stand, Water Efficiency and Sanitation Standard. It's been in that document, I think since 2017, if I got the year right.
Very cool. Yeah, I was going to say, I was actually traveling at one point into the Seattle market, and we started talking about the water demand calculator in Appendix M, and I asked the engineers there, I said, how does that make you feel? And they laughingly said terrified, because they're so used to this hunter's curve mentality that we have to be undersizing these systems. And I just thought that was really funny. So the next one is, you touched on this towards the end, energy savings versus health and safety. And, you talk about, stagnant water conditions. And as we all know, building codes in general, center around occupant health and safety first and foremost. Another thing that we bring up, and I guess this isn't really so much of a question, but it did get brought up in the questions there. A lot of times the mixing valves, whether it be electronic mixing valves, thermostatic mixing valves, they all have minimum flow requirements. And so it might not be a health and safety issue, but if you're not meeting minimum flow requirements of the mixing valves, obviously you're going to run into some issues there too. I don't know if you have any thoughts on that one.
Actually, that's a great question. And I would refer folks back to that IGC 384, I think, if I remember my numbers right, because that standard. And IGC is basically a little bit of a different process than ANSI standard. And IGC takes about 3 to 5 months to create. It's a more small group creation. It's not an ANSI standard, just to be clear. But a lot of IGCs end up being used as seed documents for the ANSI process. So the goal is to end up with an ANSI standard for a product. It's just a little bit of a different mechanism. But that IGC 384 for digital master mixing valves, the testing requirements in there, they do have minimum flow rate tests. And that's a really good point about minimum flow, because you have to have some kind of, it's all about that control of that system. So again,
Sure.
My sense is that moving forward, we're going to see a lot of movement in terms of hot water return systems, which when you look at any of the plumbing codes or energy codes, there's very minimal mentions of those systems. We're going to see, I think, a real growth in that codes and standards market moving forward, because now we're realizing that linkage to things like waterborne pathogens, which is a public safety issue, and the codes,
Sure.
It's all about public health and safety. So closing that loop, pun intended, and making sure that we're making these systems as safe as possible is a really vital piece moving forward.
Yeah, perfect. And I've actually run into a number of our engineers that have actually gone to bat with the local AHJs and stuff like that, talking about leaving the recirc on all the time. Obviously they're worried about their systems functioning with the minimum flow requirements of these mixing valves, but also they go to bat with the AHJ under the premise of the waterborne pathogens and the stagnant water scenarios, and it really makes a big difference. But along those same lines, we had another question. It said, how do you recommend satisfying the new 2021 IECC, the International Energy Conservation Code, if I remember correctly, asking for a return temperature of no greater than 104 and flow sensors? Are you familiar with that one, Christoph?
I'd have to look into that one a little bit.
Okay.
You know, with the flow sensors, I imagine a lot of that kind of revolves around the sort of the aquastat.
Yeah, I wasn't familiar with the 2021 there with the flow sensors, but I know with IECC, I think it was 2018, they were requiring aquastats and/or occupancy sensors, basically for on-demand. They were even talking about using heat trace tape as opposed to recirculation in some scenarios, and I mean it was pretty wild. And so you know, I know there are a number of states that are dealing with IECC. But yeah, I thought it was an interesting question in general.
No, and that's what I would point back to, is that the UPC and that code exemption. That code exemption for the UPC was added with a couple of documents that provided a basis for continuous recirculation. One of them is the OSHA technical manual on Legionella. That's a free download. I would highly recommend that one as a download. You can point to that, and I think some engineers have done that. Now you have the UPC, which is a plumbing code. It's an ANSI. It's actually the only ANSI plumbing code that follows an ANSI accredited process. So you have a group of technical experts, and they added it in there. So you have now, you know, a code that follows an ANSI accredited process. You have an OSHA technical manual, and the ASPE, again, going back to the ASPE Legionella design guide. That document in itself also indicates that you want to have continuous recirculation. So there's 3 documents out there now that talk about making sure these systems run continuously. I wrote an article about that. Actually, if I say would love to come back and I can touch on that article a little bit too and have it, but I can send you the link for those of you that are interested, where I touch on that subject as well. That was in Plumbing Engineer magazine that I wrote that article. So I think it's going to be, unfortunately, a lot of the energy code creators don't have a plumbing background, and so they've made these decisions from an energy code standpoint that could potentially negatively impact plumbing health and safety. And so I think we're going to see a lot more conversation and discussion on that nexus point. And I think that's going to be one of those things, maybe be at the top 11th, the 11th thing on my top 10 list. That's going to be one to follow, because that's going to be a real point. And again, you know, if you want to maximize energy efficiency while maintaining safety, you really want to make sure that the engineering is fine-tuned. That's a real starting point. And that goes back to Hardy Cross and all the rest of the topics I discussed.
Perfect. So I do want to mention too, in the chat window, we actually put links to the water demand calculator as well as the design guide reference, the Legionella design guide. So there's links in the chat window for that, for those of you that are still on board here. And there's actually the link to the standards newsletter as well that Christoph mentioned also. I think at this point, we're going to cut it off. We do have some more detailed questions that I think would put us into tomorrow if we answered all of them. So we really appreciate the engagement from everybody. This has been an awesome webinar. Christoph, thank you so much for your time and your patience. We would love to have you back. I think this was an awesome webinar. And yeah, everybody, thank you so much for your time. And yeah, guys, have a great day.
Thank you, Christoph.
Thanks, Christoph.